Hello everyone, we have been studying statistical mechanics and we have studied 3 sections. In the first section I had made an introduction on statistical mechanics or microcanonical ensemble. In the second section I had given the idea how to find thermodynamics from the number of microstates omega or by using the equation S is equal to k log omega. And the third section, with the aim of finding out the equation of state of an ideal gas, we have discussed the phase space. The phase space concept has been discussed in the third section. What is a phase space and how you can find omega for a continuous energy systems. Ideal gas means it is a continuous energy system having energy E is equal to, we are studying about non-relativistic ideal gas, therefore the energy is given by P square by 2m. Now I will have n particles, therefore the total energy will be equal to sum of I is equal to 1 to n pi square divided by I to 3 1 to 3n pi square divided by 2m. I will assume that all the particles have the same mass. I will assume that all the particles will be having the same mass. Therefore, my aim is to find out omega for an ideal gas. Actually, this was first given as a mathematical formulation, and only then we will be checking it experimentally. Therefore, how to find this how to find the equation for an ideal gas by using the basic ideas of statistical mechanics. Therefore, omega, you have already seen that omega is equal to the phase space volume divided by the minimum volume, phase space volume divided by the minimum volume. Therefore, what is the phase space volume? In the last section, I have shown you that the phase space volume or omega was equal to phase space volume, that is d cube p d cube q whole raised to n divided by h raised to 3n, whole raised to n. Therefore, this is, we are dealing with energy E is equal to p square by 2m. P square by 2m. Therefore, there is no potential energy part there. Therefore, kinetic energy is purely connected with the total energy. Therefore, these two can be separately integrated. Therefore, we will have V raised to n and I will say V 3n divided by h raised to 3n. Therefore, this is what we require is this, how to find this V 3n. You can refer, I am not going to derive that, I will be directly using that formula. That formula is derived in Patria, Kersen, Huang, etc. in the appendix. Therefore, I will be directly deriving that equation. That equation is given by pi raised to, this is the 3n dimensional volume for the phase space or 3n dimensional any type of volume, pi raised to 3n by 2 r raised to 3n divided by 3n by 2 factorial, 3n by 2 factorial. Why this is having such a very obscure formula? Why you are having such a very complicated formula here? Very complicated formula. Okay, look back into the equation, pi raised to 3n by 2, r raised to 3n and 3n by 2 factorial, 3n by 2 factorial. This is the volume. Therefore, why for here this volume is given by volume of the momentum sphere is given by, once again I will write pi raised to 3n by 2 r raised to 3n divided by 3n by 2 factorial. This is the volume for 3n dimensions. Why we are bothered about this 3n dimension? This is actually whatever properties that you study in your statistical mechanics, this is the effect of all the particles. It is not the individual effect. You have all the particles are collected together and those, the average effect of all the particles we are finding out, and that will be different from individual effect. individual effect and the average effect of n particles will be different. That is why you have such a formula. For example, this is actually the formula for your ordinary sphere for if n is equal to 1. For n is equal to 1, I will get V3, the volume will be given by pi raised to 3 by 2 r cube divided by 3 by 2 factorial. And what is 3 by 2 factorial? That is pi raised, I will write pi raised to 3 by 2 r cube divided by 3 by 2 factorial is 3 by 2 into half factorial. Half factorial is root pi divided by 2. Therefore, there is one root pi here, pi raised to half, one pi raised to 3 by 2 there, 3 by 2 minus half, I will get pi r cube is here, and what I have is 3 by 4 in the denominator, which I can write that as 4 by 3 pi r cube, 4 by 3 pi r cube. Therefore, this is the, if n is equal to 1, I get the my old equation for the volume of a sphere. Therefore, what I am taking is, in the phase space I am finding out the volume of a 3n dimensional sphere, the effect of the whole particles. The effect of an, I told you earlier, the effect of an individual in a society will be different from effect of large number of people. Together, the effect of n people, number of people if it is n, the effect of n people and the effect of one person will be different. If the total impact of all these will be different from individual people. But and for that we have finding out this equation, the effect of 3n particles or n particles having 3n dimension. N particles, each particle will be having 3 dimensions, and that formula is given by pi raised to 3n by 2 r raised to 3n divided by 3n by 2 factorial. And what is r? R is the radius of the momentum sphere, which you will be able to find out by using the equation sigma pi square by 2m is equal to, that is E, the total energy I can say, then the sigma pi square is equal to 2me. The sigma pi square I can replace that by r square, that is equal to 2me. Therefore, r is equal to 2me raised to half, 2me raised to half. Therefore, this I can substitute in my formula, general formula, and then I will be able to find out this pi square is equal to 2me, p square is equal to 2me. I can substitute this equation in my V3n. Therefore, my equation will become pi raised to 3n by 2 root of 2me whole raised to 3n, which is 2me whole raised to 3n by 2 divided by 3n by 2 factorial. This is the volume of n particles, each having 3 dimensions in the momentum sphere. Therefore, my total number of microstates will be given by, this is my ordinary spatial volume, this is my momentum volume v raised to n pi raised to 3n by 2 root of 2me whole raised to 3n divided by 3n by 2 factorial, and this is my minimum volume. This is my minimum volume. Now, I have this v is there, h cube is there, I can take them together, v by h cube whole raised to n. Then pi is whole raised to 3n by 2. 2me is once again, because of the square root, it is 2me raised to 3n by 2. Therefore, I can take that pi inside the bracket, I will be getting 2 pi me whole raised to 3n by 2 divided by 3n by 2 factorial. This is your omega for an ideal gas, where v is its spatial volume and the other part will be h cube is the minimum volume for a single particle, and the other part will be giving you the momentum volume. Therefore, I want entropy. My aim is to find out, or my aim is to show that the pressure will be equal to nkt by V and E is equal to 3 by 2 nkt. Therefore, what I want is omega for an ideal gas. I found that omega for an ideal gas, and I will be substituting that back into my equation, the Boltzmann's bridging equation, to find entropy from omega. Therefore, k log omega is the equation for entropy. I can substitute my omega back. Therefore, k log V by h cube whole raised to n 2 pi me whole raised to 3n by 2 divided by 3n by 2 factorial. And if n is very large, you can have Stirling's approximation. Log n factorial is equal to n log n minus n, n log n minus n, only for large n, and that is a very important point. You will be getting, or what it indicates is that your statistical mechanics finally you will be getting only by taking n as large, you can apply Stirling's approximation, that is log n factorial is equal to n log n minus n. Only then finally you will be getting the equation for entropy, and from that entropy equation you can find the pressure, which must be equal to nkt by V, and E is equal to 3 by 2 nkt. Therefore, the equation that P is equal to nkt by V and E is equal to 3 by 2 nkt you got only by taking n as a very large quantity. Therefore, whatever techniques I use in statistical mechanics, that is applicable only for a large numbered system. Or statistical mechanics works for only large number system. If you have some 100 particles or 20 particles or 500 particles, the statistical mechanics will not be working. It will be working for millions of particles only. For example, electrons inside the sun, photons inside the sun, or you have even you have some electrons inside a small metal piece. For example, electron density is nearly 10 raised to 28 electrons will be per meter cube inside copper. In copper you have 10 raised to 28 electrons per meter cube. If you convert that into centimeter cube, 1 centimeter cube of in 1 centimeter cube you will be able to get 10 raised to 22 electrons will be there, dividing by 10 raised to 6. Therefore, in 1 centimeter cube you have 10 raised to 22 electrons. Therefore, you can very well apply statistical mechanics for studying about electrons in copper, so that you can study about diamagnetism, you can study about electrons in iron, you have ferromagnetism, you can study about electrons in aluminum, you will have paramagnetism. This is how you apply statistical mechanics, but you can apply only for large numbered systems, That is the basic point that you have to remember. Yes. Therefore, you can supply n log n, you can use that equation n log n minus n. Therefore, this equation will become S is equal to k log V raised to n. This n is common factor here. This log 3n by 2 factorial, I can take that as log n factorial. Therefore, minus log, it is n factorial. Therefore, that is log 3n by 2 factorial. Therefore, I can replace that as minus log 3n by 2 factorial, which will be equal to 3n by 2 log 3n by 2 minus 3n by 2 minus 3n by 2. And substituting, I will be getting a long equation like this, log nk log V by h cube. Yes, that is this part, nk log V by h cube. K nk log by 2 log 2 pi me, and that is this part, and then minus 3n by 2 k log 3n by 2, minus of minus will be giving you 3 nk by 2 plus. Therefore, that is my expansion of my log omega, and then you can have this nk log V by h cube is there. You have 3 nk by 2 is here and minus 3 nk by 2 is here. Therefore, 3 nk by 2 I can take outside. Therefore, log 2 pi me minus log 3 n by 2. Therefore, 2 pi me log a minus log b will be equal to log a by b, and 3 by 2 is a common factor. I can take that to the this here exponent form, and then I have 3 nk by 2. This is my S. This is the equation for entropy. This I can rearrange. If I want, I can take this nk as a common factor. I can take this 2 pi me divided by 3 n by 2 whole raised to 3 n by 2 together. I can rewrite my expression and then find out what is S. As a single equation, I will be able to write, plus I will be having plus 3 nk by 2. From this, I will be able to find out what is my pressure, what is my energy, etc., or what is my temperature, etc. For example, I have this. I will find out what is the equation for my pressure. What is the equation for my pressure? You have only V here. V is only in this part. Therefore, all these parts are constants. Therefore, I have nk log V by h cube. H cube is once again a constant. Therefore, what my equation for entropy of an ideal gas is given by S is equal to, this is the only thing that I am interested, Nk log Cv, Nk log Cv, where C is given by 1 by H cube. Therefore, if I want pressure, my P by T is equal to dou S by dou V, keeping N and E as constants. Therefore, Nk log C differentiated, that will go and become 0. Therefore, Nk divided by V, on cross multiplying I will get P is equal to Nkt divided by V. Therefore, from my previous equation for entropy, I am able to get back my equation for pressure of an ideal gas, which means I can get my equation for an ideal gas, which I had already derived in obtained in thermodynamics by using kinetic theory of gases. Once again, I will be getting that back in statistical mechanics, or my statistical mechanics has been tested. Once tested, once again I am going to test. I am going to find out what is my energy, and if I get back my 3 by 2 Nkt, I will be satisfied. I am once again checking something like checking the vaccine. I am once again doing it, and if I get it once again, then I will be able to apply my equation for omega. I can find omega for any other system and then find the properties of the system. Okay. From here, what I have is Nk log V by H cube, and my aim is now to find energy. Therefore, I will be using dou S by dou E equal to 1 by T. Therefore, I am taking partial derivative of energy only. Therefore, I have Nk, this is not important, that is also not important. This Nk log some constant E raised to 3 by 2. That is the only thing that I require, that is S is equal to Nk log C E raised to 3 by 2. That is, I can write that as Nk log C plus Nk log E raised to 3 by 2. Do not worry about what are the other parameters, just because this is a partial derivative. This is a partial derivative. Therefore, do not worry about what are the other variables, because you are finding out this temperature 1 by T, just like dou S by dou E, keeping N and V as constants. That is why all other parameters are now not there. Therefore, what I have is, this also is not necessary. What I have is 3 by 2 Nk log E. This is my S. All other parameters are not necessary. It may be there, but I am not interested. Plus, you can put all those things as another new constant. Do not worry about the constant, because what is the variation of the constant with respect to energy? Constant never varies, it will be equal to 0. Therefore, if I take a derivative of S with respect to E, I will be getting 1 by T is equal to 3 by 2 Nk divided by E. Cross multiplying, I will get E is equal to 3 by 2 Nkt. 3 by 2 Nkt. This is the equation of state or energy of an ideal gas. Therefore, we have tested, doubly tested the application of, or the equation of a microcanonical ensemble. We applied that for an ideal gas, and we got back all the equations that we got in thermodynamics using kinetic theory of gases in statistical mechanics for an ideal gas. Now, our statistical mechanics microcanonical ensemble method is open for any other system. You can apply this, the equation S is equal to k log omega. The only thing that is necessary is you have to find out omega for any other system. You find omega for electrons inside a metal, you will be able to find out susceptibility, diamagnetic, paramagnetic, ferromagnetic susceptibility. You find out omega for electrons inside the sun, you can get the ideas of white dwarf. You find omega for, that was omega for photons inside the sun. That was what was done by Max Planck. He found that omega for photons inside the sun, the number of microstates for photons inside the sun, or for black body radiations. Any hot body, it will be emitting radiations, and it will be giving a distribution law that will be going on increasing. This was Planck's distribution, the first way of using statistical mechanics. This was the Planck's distribution or blackbody distribution. Nobody was able to give. This was experimentally observed well back in 1750, but up to 1900 nobody was able to give an equation for that. It was Max Planck, by using the equation S is equal to k log omega, which was developed by Boltzmann, he was able to give a proper equation for this blackbody distribution curve, the famous intensity distribution curve. U of nu d nu is equal to 8 pi h nu cube by c cube into 1 divided by e raised to h nu by k t minus 1, e raised to h nu by k t minus 1. Yes, that was the equation that was developed by Max Planck. That was an equation that changed this world. From 1900 onwards, the whole science changed, whole physics changed. We have computers, we have electronics were there, all types of instruments except the electrical equipments. All electronic equipments were developed after this development of the equation for blackbody radiations. Max Planck put forward that equation, and then later in 1905 Albert Einstein explained photoelectric effect. He also explained the Brownian motion of suspended particles, which made sure that atoms exist. Then came all other discoveries. Quantum mechanics came, computer science came, all other things came after this discovery by Max Planck, the explanation for blackbody distribution, and all is because of the Boltzmann's equation S is equal to k log omega. Now we are ready to test this equation for any other systems. Before that, we will work out some problems. Yes. For example, first problem, n atoms of an ideal gas are enclosed in a container of volume V. The volume of the container is changed into 4V. Volume is changed into 4V while keeping the total energy constant. Therefore, we have omega is proportional to, we have already seen that omega is proportional to V raised to n. Your energy E raised to 3n by 2 is a constant. Therefore, do not worry about the energy. Omega is simply proportional to V raised to n. Therefore, S1 is equal to k log a constant into V raised to n. I will take all other things as constants, k log C V raised to n. And S2 will be equal to k log C. Here volume is changed to 4V. Therefore, 4V whole raised to n, not it is typed V there, it is n. Therefore, k log C 4V whole raised to n. Therefore, what I want is S2 minus S1. Therefore, n k log C 4V divided by n k log C V. Therefore, what we will have, C and C cancels, V and V cancels, what we will be having is n k log 4. N k log. That answer was a tricky one. In units of n k log 2, what will be the change in entropy? What will be the change in entropy in units of n k log 2? Therefore, your unit is now n k log 2. Therefore, how many times that change will be there? 2 times. 2 times. This was asked for the gate. Therefore, it is 2 times. It is 2 n k log 2. Therefore, it will be, the change in entropy will be equal to, the answer is 2. The answer is 2. Okay. This is another question. The internal energy of a system at a fixed volume is found to be, depending on the temperature, T as equal to E of T, A T square plus B T raised to 4. What is the entropy? What is the entropy? How will you find the entropy? TdS is equal to, here energy is not depending upon volume, it is a function of only temperature. Therefore, volume is not coming there. Therefore, you have TdS is equal to dE, no volume is there. Therefore, ds is equal to dE divided by T. You are given E. Therefore, differentiate that. You find dE, that is, this will be equal to 2AT dt plus 4BT cube dt, and then divide that by T and then integrate. You will be getting the answer. The answer will be 2AT plus 4 by 3 B T cube. Okay, these are some simple problems that I have given to you. How to find this omega for an ideal gas? What we have discussed is how we can find omega for an ideal gas, and from that omega we can find the thermodynamic properties of an ideal gas. and we have demonstrated that it is very easy to find it. The only thing is that the equation looks to be a very complicated one, but that equation is not at all a complicated one. It is a simple equation. Only thing is that you have to remember that it is for a effective, the total effect of the n particles in the 3 dimension. That is what we are using there, and that volume, the general formula you will be able to apply, and then from that volume you will be able to find out omega. Therefore, in this session we have been dealing with how to find omega for an ideal gas. We have found that omega can be found by using the equation for that momentum volume multiplied by position volume divided by that minimum volume, and that equation looks to be a very complicated one, but actually it is the effect of n particles in the 3 dimensional system we are using, and that is generally given by pi raised to 3n by 2 r raised to 3n divided by 3n by 2 factorial. Using that equation we can very easily find out what is omega, and from omega we can find the entropy, and from entropy we have verified that for an ideal gas PV is equal to nkt and E is equal to 3 by 2 nkt. Now we are ready to use this equation for finding out the properties of any other systems. Okay, that the remaining things we will be studying in the next session. Okay, today we will wind up.